Hi, we're going to look at the next question, which is about a set S with n elements. The number of ordered pairs in the largest and the smallest equivalence relation on S are. So there are a few things that we must look at here. There's something called an equivalence relation, and there's a set S given with n elements. And the question is, what is the least possible elements that S can contain, and what's the maximum possible elements that S contains? So let's discuss this now. Alright, what's an equivalence relation? If you do not know what an equivalence relation is, now is the right time for you to pause this video and then browse for it, learn the definition and then get back. So an equivalence relation, let me define it quickly, is something that satisfies, given a set S, you consider all ordered pairs S cross S, take a subset T of this S cross S. This particular T is said to have the property reflexive if given any A from the set S, A comma A must belong to S. That's the first property. The second property is symmetric. When you are given two elements A and B in which belong to S, not S, it's T, S cross S, which is T, a T which is a subset of S cross S. If A comma B belongs to T, then it must imply that B comma A also belongs to T. The third property is the most important property. It's called transitive property, which means if AB belongs to T and BC belongs to T, then it implies that AC belongs to T. So there are three properties. One is reflexive, which means for every A comma A belongs to S. I'm sorry, I made a mistake here. It's not S, but it's T. It is T. Alright, that's reflexive. Symmetric is when A comma B belongs to T, B comma A also belongs to T. And third one is transitive, when AB belongs to T, BC belongs to T, then AC belongs to T. Alright, with this let's go to the question. The question says S is given, as you can see, any subset T of S cross S cannot be a equivalence relation. It must satisfy the three properties that I discussed earlier. Only a few sets satisfy such properties, and such subsets are called equivalence relation. As you can see, the reflexive property says that for every A in S, A comma A must belong to T, which means assume S has n elements. Then each of these n elements, each of these, let's say A1, A2 up to AN, are precisely the elements that belong to S. Alright, which means for every element that belongs to S, AI comma AI must be in T, which means let's go to a new board, which means AI for every AI that belongs to S, it implies that AI comma AI must belong to T, if you think of such a equivalence relation T, which means if you pick any equivalence relation T, if you try to form any equivalence relation T, the number of elements in T, this symbol stands for the number of elements in T, must definitely be greater than or equal to n, which is the number of elements in S. Let the number of elements in S be n, then the number of elements in T must at least be n. T has at least n elements because of the reflexive property that it satisfies. At least n elements. Now, what is the maximum number of elements that T can have? T can have at the maximum, what is T? T is a subset of S cross S. Consider T to be equal to S cross S. This is definitely a reflexive relation because it has AI comma AI. It is definitely symmetric because whenever a comma b belongs to T, b comma a also belongs to T. Trivially, you know, you have all the elements of S cross S, which means it has to have all the elements. Whenever a comma b belongs to T, b comma a also belongs to T. We are obviously satisfied. Third thing is, whenever a comma b belongs to T and b comma C, if these two belong to T, then AC belong to T. Forget that, you know, every single element belongs to T, so there's no point in even worrying about whether these points are true or not. Obviously all these points are true, which means T has, or T can have, how many elements are there in S cross S? The number of elements in T can have at the most n square, and in the previous case we saw that it has at least n because of reflexive property, which means, get the question properly, given any equivalence relation T, it must definitely have at least n elements because of reflexive property, and at most it can have all the elements. If you put all the elements of S cross S, it is obviously an equivalence relation, which means, let us conclude that any equivalence relation, let me write that down, any equivalence relation on a set S with, say, n elements must have at least n elements. What should have at least n elements? The equivalence relation, the T in our previous discussion. Any equivalence relation on a set S with n elements must have at least n elements, and can at most have what? Have dash elements, fill up the blank space, n square elements, because it can be the whole set. So now, as you can see, let's get back to our question. Let S be a set of let me open this. Let me open the annotation mode. As you can see, let S has n elements. The number of ordered pairs in the largest and the smallest equivalence class on S are obviously n square and n, at the most n square and at least n. So B is the right answer.